And he's going to tell us about quantum simulations with superconducting qubits.
Thank you. Yes. I don't know what I said in the abstract, but we might deviate from that to some extent. Usually I show a picture of dilution refrigerator or superconducting qubits. Those are the most beautiful thing I have ever seen. But my worldview of what is the most beautiful thing changed overnight last night, so I'm updating it. I want to thank the organizers for creating such a stimulus conference in such a beautiful place. I'll also especially thank them for giving me a chance to be a panelist yesterday. And yesterday, all the time I need to share my philosophical worldviews and my grand vision of the future, so I don't need to put any big picture of how future is supposed to look like or what we are doing, why we are doing it. So I said everything I needed to say yesterday. So from the several works that we have done after supremacy experiment, I chose one, and I'm going to talk in details about that particular one, which is a recent work, and a few days ago it got accepted to Nature. And the point of it is that I want all of you to understand what that particular work is about. I gave a talk on it several times, and I totally failed. No one understands. So this is my third attempt of giving this talk. Let me just tell you what the physics is about. And we're going to go slowly over this, so you can ask questions even in the middle if you want. And if we end up soon, then I can add another manuscript that we did, another project we did. That's much simpler story to explain, so I can explain that more rapidly. But it depends how we're doing it in time. Okay, the story I want to tell is based on this archive work, and it's done in collaboration with Vedika and Matthew and Elliot and Jesse from Stanford. This is the after decades of playing with unitary gates, if you look at the articles and projects and things we do, most of them is we do unitary sequence and then we do measurement. But when you're thinking about the error correction, measurement, and unitary evolution, they just come together. They happen not one after the other, but they are interspersed with each other. And this is really where we need to go. In fact, the measurement is half of quantum mechanics. And the deeper level, or the more philosophical or more historic level, there is a disjoint, there is a problem called measurement problem. A measurement problem says that we have two prescriptions for quantum mechanics. One, it says that the wave function evolves according to the Schrödinger equation, and then there's another prescription which tells you what happens during the time of the measurement, which is the state of the system partially or fully collapsed to an ion state of the measurement operator. And to reconcile this together, the multi-word interpretation and all these things coming together. So there's an active issue to understand how these things together and try to merge them together or try to come understand them together. And they have been discussed in the context of error correction, and then very recently people, physicists start to picking on them, and they start looking at the threshold, error correction threshold theorems that they understanding with the lens that we are very good at it, the phase transition, and try to say that these error correction threshold theorems that computer scientists have been talking about is nothing but what we physicists usually refer to as phase transitions. Works of Michaels and others is in that regard. But when it comes to actually doing the experiment, there are challenges. There are several challenges in here that I'm listing. And one challenge that we are always facing is that, well, we are dealing with open quantum system and a noisy quantum system. We have what is stable and what's not stable, and can we realize any of this? The good news is that there are lots of theoretical work which suggests that a simple circuit like this captures many of the physics that we are interested in. So the circuits we are going to explore are composed of unitary gates. These are the blue elements, and the measurement interspersed through the circuit. And we want to know what happens, what kind of structure of the wave function you are going to get at the end of such an evolution. And you can see intuitively if the number of the measurements, if the density of the measurements is very low, you have your typical unitary evolution, which most of the time could lead to ergodic states. But if you start to add the percentage of the time you interject measurement, then you're going to kind of get a Zeno effect, and your state is going to get locally purified, and if you do too many times, the entanglement doesn't have a chance to propagate. So you're going to end up with a different type of states. Hence the notion of phase transition that comes into mind, and we are going to see it together. But there are many different challenges, or there are actually, well, there are two, let me just list two in this experiment. One that has been extensively discussed in the literature, probably you're familiar with, is called the post-selection measurement. Meaning that we are not interested in doing these measurements and averaging over the outcome, just locally project and just repeat the experiment and look at the ensemble of the results. When you do a measurement, when you choose to do a measurement, you have to get these outcomes out, and when you repeat the circuit, you only have to consider the circuits, and you have to average the circuits together, you have to bundle the circuits together that are exactly showing this sequence of outcomes. So you are really kind of after exponentially small number of the outcomes, whatever you choose is not going to appear many times, right? Most likely it will be exponentially small chance to see the exact same sequence. This problem is usually referred to as post-selection measurement, and there's lots of effort to see how to overcome that, because the physics that we're interested in, again, comes from sticking to a single quantum trajectory. Experimentally, at least for the superconducting lab, we have another beautiful problem called mid-circuit measurements. Mid-circuit measurements meaning that the size of these measurements, if I had to scale them, it's 10 times longer than the size of the unitary operators. So the measurement takes much, much longer time. So if I interject a couple of measurements, the rest of in one qubit, the rest of the qubit got to wait as that measurement ends, which takes substantial time. So what are we going to do there? Yeah, these are the challenges we have. And I was feeling very desperate on what to do and what can be done, till I came across this commercial, which actually told me actually what to do very clearly and very precisely. And this is what the subject of this article is, which says that you can use a space-time duality. Space-time duality is not a favorite thing to do, and I explain to you in a second what it is, when you are thinking about dealing with unitary circuits. But in plain language, meaning that you replace the space and time in your circuit, meaning that when you're thinking of these sets of instruction as a circuit, you say these are my qubits and this is time. Now think of them as your qubits and this acts as your time. It's as strange as it sounds, usually it's not a very clever idea, right? Because the space-time dual of a unitary operator is not going to be a unitary operator in general, so you're really adding more headaches to it. But in this work, I'm trying to tell you that there are cases that are this space-time duality is useful, and start building intuition from there, and then we push the limit of the phases that we can understand by this trick. And it, to some extent, helps with post-selection problem, but at the end of the talk, you see I got stuck with this post-selection problem. So I pushed the boundary, pushed the limits, but at the end of the day, we are not claiming that we are solving the real major problem that community is struggling with. So here I'm showing you the space-time dual of a this 1D circuit. So you see, the idea is that this is a transformation, this is a mapping that it allows you to go to a higher dimension. So space-time dual of the circuit that I consider here is a 2 degree of qubits, generally. And the measurements now are all piled up at the end of this. And if I call this axis my time axis, and the other two axes qubit axis, now you see how lots of, all the measurements have been diffused to the surface or diffused to the end or accumulated at the end, however you want to intuitively think about it. So we are going to deal with this mapping. Whenever we are given this thing, we are just going to map it to here because this is the good old thing that we can do. So this is the game we are going to play over and over again. And it kind of makes sense to do this, or it's not a very bad thing to do it, because as I said, this, the time, space-time dual of a unitary is not a unitary. But here you don't have unitaries to begin with. You have these mixture which are non-unitary operators. So you are not missing much, so it may kind of make sense to do it. So let me walk you through an example which is actually a bit simpler than what my general case that we are going to get into. Let's say someone wants you to know, ask you what is the structure of the state of the system after if you have 12 qubits and you evolve them up to 5 or 6 or 7 layers of gates, and these gates or these operations are a mixture of unitary and non-unitary operators. So this symbol means that every step I do an action which is a mixture of both operations. So let's suppose someone asks you, what is this outcome? Well, let me do a little bit of math, and then this gives us inspiration of how to solve this problem. If you were given a unitary operation, as I said, if you take the space-time duality transformation of it, you end up with an object which is not necessarily unitary, right? So you're switching x and time, and this can sort of just become a weird thing. However, this unitary become a weird object, not unitary. However, there's a nice decomposition for it, which says that it can be written as a product of a unitary and a non-Hermitian, an H, which is Hermitian but not unitary. So now we are going to twist the problem and say, what if someone asks you this? If you ask me this, I confine you, I put this constraint on you to ask me this question. If you ask me this question, then I say, oh, I go space-time duality, and then I solve the problem. So for a very limited group of problems, set of operations that I tightly control what you ask me, the space-time duality of a non-unitary action is a unitary thing. So by going 12 qubits depth 6, we can go so depth 7, you can go depth 7 qubits depth 12. This is after the transformation, and now you can see that this is free of any mid-circuit measurements. So there's no mid-circuit measurements in here, so we are in better shape. Except now we run into trouble that the information, the state of the system we are interested in, is laid against time axis on the 7th qubit. That can be handled by introducing a swap network, which takes this information which was laid down in here and bring it out in here. So circuit A, B, C are equal to each other, and now you have the choice of doing any of them you like. So it's subject to the constraint that I tightly confine myself to choices of this that I know the unitary transformation, the space-time dual transformation is unitary, and then I swap network, and now this is my information that I'm interested in, and we are going to go at the cost of introducing 12 extra qubits and going to deeper circuits. We are going to do this circuit, and we are going to, after those beloved area law and volume law converse things that has been mentioned. So in this case, which I'm doing as a warm-up, and here I'm showing you for what circuits it works and what not. So again, it's not a general solution. We are not solving a measurement induced for real, but for a very small subset of qubits, a small subset of problems. You can see for the different choices of theta and phi, which goes to the unitary and whatnot, you can see the volume law of entanglement entropy, which is this is the Page curve, and then usually this is the area law they talk about, but in this particular case is a log entropy or something. It's not exactly area log. This is meant not to be flat. So entropy of subsystem increases, and then when you come to the full system, the entropy comes back to zero because the whole system got to be pure. And this is, by the way, measured by randomized measurement technique. So the information that we want here after cellular mapping comes available to us. So this is a very small showcase of how these things is working for a very limited set of problems. So let's get more real. Let me maybe go back in here for a second. So I'm going to do cheating, but less cheating than before. And that is, well, if you look at these circuits, right, these are the very, very familiar supremacy circuits that we have done, meaning that there's 2D layers of unitary gates followed by measurements. But now we are going to partially measure some of the qubits and see what they stated. So if I solve this problem, this must have been the mapping of the 1D problem of more general problems. So I'm going to go now to do what we are good at, meaning the group of 2D unitary gates in 2D, and at the end of the day do some measurement and see what is the nature of the eigenstates remaining here. And I'm going to claim you that if you go to the inverse mapping, you are actually solving a measurement-induced a 1D problem that has measurement in between. So what this is a mapping of, it looks a bit ugly, but the mapping exists all the time, the mapping exists. So we are not, just want to get it clear, we are not solving a measurement-induced problem in 2 dimension because all the measurements are piled up at the end. What I'm saying is that this is a mapping of a 1D problem which has measurement in between gates, and we are going to do that. Because at the end of the day, what matters is that we change the ratio of the number of unitaries to the number of the measurements. And this ratio is really sets the physics, regardless of how complicated the mapping is. And if you go through all this, you will see things that make sense, starting from let's say, Riemann entropy of subsystem size. So this is the 1D case that we are considering, 1D wave function that we are considering along these few qubits. And you can see the entanglement entropy in this 1D structure at shallow depths is area law, or rather, there's no entanglement entropy. But as you go, as you increase the number of depths of the circuit, meaning increase the percentage of the unitary gates, you go deeper and deeper, you are getting to this volume law, and you see there is a clear jump between a step, 3 and 4 to do there. So if you do 4, you're really doing this, the shape of the structure of your state of the system is very different than shallow depths. I want to introduce something maybe more intuitive, and we're going to pick this later. And this is the notion of mutual information over a subsystem. A and B, A is the subsystem of qubit 1 and 2, and B is the subsystem of 2 other qubits. And you can see they can be at various distance from each other. So you can see the same physics in here that at shallow depths, the mutual information between these two subsystems, maybe I flash it for a second. Just look at this. This is subsystem A, this is subsystem B, and you can see B can be next to A, distance 0, or it can be slightly away, all the way to distance 3. So, sorry, I'm missing from that slide. This is subsystem A and B. So at shallow depths, there is no chance for A and B to talk to each other, and their mutual information between them is 0. When you go to deeper and deeper circuits, then there's a uniform mutual information between them, regardless of their separation. Here you see, there is a slightly, at shallow depths, if they're close to each other, there is mutual information between them, but when they're distant from each other, there is none. But then after you go through the transition, transition, I have a small system, then you see totally change of behavior, and regardless of what depth you are in or what separation you are in, the mutual information is a fixed number. More of the same. I'm changing the geometry and changing the separation and whatnot, and you can see the same physics. So this is a cut through the page, through the one that I showed the last slide. That after and this area law and volume law is our suggestion of what is happening. Is not any concrete outcome of the experiment. It's just very suggestive. But here you can see, for instance, when you're at shallow depths, number of unitaries is very small. The mutual information between subsystems depends on their separation. And you go to very deep, then the mutual information becomes independent of the separation. Okay, I've been going very slowly. That's good. That's good, then I don't need to go with the other talk. So this is the part that everybody gets lost, so let me go over it very slowly. So we're going to stop in here because I didn't do the good job of dealing with the post-selection problem, meaning that this physics is obtained, I think you see 12 qubits over there, and I have to select from 12 outcome of 12 qubits, meaning 4,000 measurements, so you've got to do millions and such of measurements, and only with the probability of 1 over 4,000, you get the correct bit string. So many of the bit strings we are getting goes away. So post-selection problem is really beating us. So I'm going to switch to a hybrid method to continue slightly further and to go to 70 qubits. So we are going to do the same physics, same measurement. And what we are going to do is to also get help from a classical computer to understand the entanglement structure pattern of the system. Meaning that you choose a group of qubits to do measurement on it, and based on your choose a decoding radius, and up to a given radius that you choose, you use these you do measurement on them, and you feed this measurement to a classical computer, and that would simplify the task of doing the physics of evolving the wave function, because you know the wave function you've got to evolve at the end has to give this particular outcome. So you simplify the work of classical computers, so you can go up to 70 qubits, and you ask a simple question: is the state of this qubit, is the sigma z of this qubit is pointing to the north hemisphere or south hemisphere? Very binary, simple question. You get plus 0 or 1, plus 1 or minus 1 from your classical computer, and you put it next to the outcome you get directly from your experiment. And this quantity, the cross correlator, the claim is that it's a proxy for the entanglement in the system. So there's a complicated recipe, and I'm not really good at providing intuition behind it, but it's captured in this figure anyways. So let me show you what it does. This cross correlator, essentially you can think about it like is a measure of how much entanglement propagated, how much that qubit is entangled with the rest of the system, and revealing, by changing the decoding radius, revealing the entanglement structure in this wave function at the end. And we know at the end of the day there's no qubit to get entangled, so this whole thing has to be pure. So if the last number is not 1, you can divide it by that number and you can get 1. So this is an argument that we use. We say that at the end there is nothing more to be entangled to, all the information should be contained, but in the experiment is not. This is a purity condition. So we impose this purity condition by hand by dividing this major correlator by this last value. But maybe it's more intuitive to talk about proxy, entanglement proxy, which is just putting this in the log form, and now you start seeing the entanglement pattern more clearly for a certain group of well-defined rho, what rho is in a second. And you can see that the entanglement of that qubit with the others drop the distance, and in the other cases stay flat and only drops at the very last point. Let me introduce this rho parameter because this is the parameter we are going to tune for seeing the phase transition or crossover rather. Rho is the number of the gates that I replace with identity there. So I'm going to go to a fixed depth, steps 5, but many times I'm going to use an identity rather than an entangling rate. Rho is the percentage of the gates that is replaced. It is the gate actually applied. Rho 1 means every gate, every time you have a chance you feel an entangling gate. Rho 0.3 means only 30% of the time. You didn't have 70% of the time. You just have identity whenever you have a chance to do an entangling gate. And again, you see the entanglement entropy dropped with the as a function of decoding radius. But as you increase the percentage or the ratio of the unitary operators, entangling unitary operators, you can see that entanglement entropy or this proxy shows you that there is totally change in the behavior of the entanglement structure in the system. You can do this up to 58 qubits. You can change this gate density, essentially tune your ratio of unitary to measurement. And you can see a very clear crossover, which tells you about the ratio of where the transition should be. Again, we are solving a 1D problem, keep in mind. Okay, in the last minute, I want to tell you, what should I tell you? Well, yeah, in 1 minute I say this and then I'm done. So I want to focus on some maybe interesting take-home message. I told you that when you get to the end of this decoding radius, you know that you have a density matrix of a pure system, trace of rho square should be 1, right? So the dividing by this very last value is equivalent to that, or enforcing the last value to be 1 is purity condition means the same thing. So I'm going to focus on these values that I just blindly divided by to get 1. What are these values? So nominally, all these numbers you see in here should be 1 for a pure system, which we don't have. And this is the numbers I divide to. But what I want to highlight and point out here, that the response of the system to this noise, external noise, coupling to the environment is very different in the disentangling phase versus the case that is entangling phase. And it can tell you again, pointing out a very susceptible wave function that you have. So if you have a highly entangled state, it's very more susceptible to external noise. Maybe not that surprising. But also another thing I want to do is that I can extrapolate, see where this is going to hit the axis, where this division would be rather impossible. And this tells me that if I had roughly maybe 12 by 12 sets of qubits, it would be impossible to do this operation, this division. It simply means that unless we improve the coherence of our devices, making devices bigger than this is very impractical, is very meaningless. You're not going to get a chance to entangle beyond this before the coherence takes over. So, goes back to stuff I was mentioning yesterday about the importance of material science and fixing the coherence issues and whatnot. And I think this experiments also point to a very practical number of how far we can push these experiments before needing to substantially improve our coherences. Thank you.
Thank you very much, sir.